Since being recruited to Imperial from Oxford last year, this image has been my opening slide at several talks, and I'm often asked if this is the view from my new office at Imperial. To which I reply, well, actually, it's the view of my new office at Imperial, as you can see. Now, I'd like to begin first by, most importantly, thanking those individuals and institutions that have helped me on the path during my medical and scientific career over the last 25 years. This began as an undergraduate in preclinical medicine at Oxford, and I then went to the Royal Free Hospital School of Medicine, where I still remember to this day the first clinical lecture given to us by Professor Neil McIntyre, who was Dame Sheila Sherlock's successor as Chair of Medicine and Head of the Liver Unit, where I was later to do my house job. And in his first lecture, he told us that more than 80% of diagnoses are made by the history alone. And that left me really wondering what the rest of the whole building of the Royal Free around us was doing, all the machinery of diagnostic laboratories, CT scans, etc. Osler made the same point when he said, listen to your patient, he is telling you the diagnosis. And the more clinically experienced I become, the more I realize the truth of that central fact. And I think that also reflects the central fact that the interaction of the physician with the patient remains not only our most powerful diagnostic tool, but it also remains an essential therapeutic tool, because ultimately it's through the agency of the physician that whatever new tools we develop or new interventions we develop are delivered to the patient. And it's the way in which the patient takes that on board and fights their illness with the help of the doctor that makes the difference. So that interaction remains a key dynamic in all our lives, I think. So at the Royal Free, as I said, the house job I did was on the liver unit. It was known as the 100-hour-a-week job, or the baptism of fire. And to this day, I have a number of very good friends that I remain in touch with from those times that felt a little bit like being at continuous war. And one of them is Prem Mistry, who I'd like to particularly thank. He was my mentor and registrar on the liver unit at the time. He's now chair of pediatric hepatology at Yale. And I was very fortunate in having him as an exemplar of the sort of compassion and humanitarian aspect of medicine at such an early stage in my career. And at the same time, in the late 80s in London, the numbers of homeless people on the streets of London were rising sharply. And I was engaged in voluntary work with the homeless at that time. And at the same time that the numbers of homeless increased, there was also a gradual but progressive rise occurring in the incidence of TB, which I'm sorry to say has continued in Britain to this day. And it was here that I encountered my first patients with TB and became fascinated by the illness from a clinical perspective. Then my first SHO job was at the Brompton, depicted here as how it looked a few decades ago. And there I was fortunate to work for Donald Mitchell, who also taught me a lot about the physician-patient interaction. And to this day, his compassion remains an inspiration to me. And within a few years of my leaving the Brompton, I realized that the venerable North Block had been sold off by the NHS and converted into some of London's most expensive luxury flats. Perhaps I should have been there a little later, I'm not sure. So I went on to be an SHO at Addenbrooke's, where Keith Peters was a very helpful mentor and appointed me to the European Society for Clinical Investigation Exchange Scheme, which gave me the opportunity to work on the intensive care unit in Basel for 6 months, which was great because it really gave me a perspective of a different type of healthcare system altogether from the NHS. I then returned to the UK to become the registrar in infectious diseases at the Churchill Hospital in Oxford, stepping into Paul Klenneman's footsteps, who at that time had just moved on to a research training fellowship. And there I'd like to particularly thank David Worrell, Chris Conlon and Tim Pito for helping me to learn a combination of systematic and intuitive approach to really diagnosing a broad spectrum of tropical and infectious diseases. And I first became research active in 1993 as an MRC clinical training fellow when I joined Adrian Hill's lab at the Weatherall Institute of Molecular Medicine. And my two mentors during the research were Adrian and Alan Townsend. Next, I was appointed as a clinical lecturer in general medicine and infectious diseases at the Nuffield Department of Medicine, which John Bell was heading at the time. And also I was made the first Sherrington lecturer in clinical medicine at Magdalen College, where I worked with John Stein and William James. And at this time in my career, I was combining clinical practice, research, and education, quite a lot of all three as it happens. And this was a key moment when I wanted to set up my own research group, the Tuberculosis Immunology Group, in 1997, and that was when I submitted my first ever grant proposal, which was to the Wellcome Trust. It was a project grant and it was awarded, and that allowed me to develop my own research program as a principal investigator. At the end of that project grant, I applied for a Wellcome Senior Fellowship, which I was awarded and held at the Nuffield Department of Medicine at the John Radcliffe for the next 5 years. So this is really the global epidemiology of TB, and the areas in dark blue or violet that you can see here, the darkest areas, these are the areas of highest incidence, and they're in sub-Saharan Africa, where the HIV epidemic is at its worst. And the reason for that is obviously that HIV greatly promotes the risk of development of active TB in people who have latent TB infection. The greatest case burden overall, however, is in Asia because of the large populations living there. And India alone, staggeringly, accounts for 20% of all TB cases in the world. This is the sort of pyramid, if you like, of the morbidity and mortality from TB. Almost 2 million deaths a year, 9 million new cases. And those staggering figures are really just the tip of the iceberg, because in fact 1/3 of the world's population is latently infected. And this is really a sad reflection of global healthcare inequity, because TB treatment is one of the most cost-effective healthcare interventions that we have. So it's a sorry reflection on healthcare systems around the world. It's also rather telling because our tools for diagnosis, treatment, and prevention are ancient. This lists the old and ineffective weapons with which we're continuing to fight the world's most lethal pandemic. In terms of diagnostics, the tuberculin skin test is 120 years old now. Sputum microscopy is a century old. Chest x-rays are nearly 100 years old. In terms of vaccination, the BCG vaccine is of limited and variable effectiveness. And the drugs have to be taken 4 drugs at a time for 6 months. And for patients with multi-drug resistant TB, the drugs are relatively ineffective, even the newer drugs, or the ones that we sort of co-opt from use in other diseases. And in patients with XDR TB, or extensively drug-resistant TB, the drugs don't work at all. And this is really, again, a sad and poignant fact, because we can't treat our patients effectively with MDR and XDR TB, and yet the most recent TB drug to have been developed and licensed was 40 years ago, rifampicin. Also, there's an interesting interaction here between these ineffective tools. So BCG vaccine, which in the first place is of limited effectiveness, it actually confounds the interpretation of the skin test, which has hitherto been our only means of diagnosing latent TB infection. So it's on account of this rather desperate situation that the latest global plan to stop TB from the World Health Organization, their latest 10-year plan, for the first time has recognized and also emphasized the fact that we're not going to be able to contain or reverse this epidemic unless we develop better tools for diagnosis, prevention, and treatment. And they've also recognized for the first time that we're going to have to get serious about tackling the latent reservoir, or this silent epidemic of 2 billion infected people, if we're really to reverse the epidemic successfully. So the foundation or bedrock of this talk, in a way, is really the natural history of TB infection, which I'd just like to walk you through now. After exposure to an infectious TB case at the top, people can, if they inhale infectious respiratory droplets that carry tubercle bacilli, then their innate and adaptive immune systems get activated. They develop a positive skin test, which signals the presence of latent TB infection, which initially is asymptomatic. 5% of people then progress early to develop TB disease, but the majority, 95%, enter a state of successful long-term immune control termed latent TB infection, or LTBI for short. Once in that state, there's a 5% risk, if you're an immunocompetent adult, of then progressing to TB disease. But that risk is massively elevated by certain factors that cause cellular immune suppression. And I'll come back to those shortly. Once you develop active TB disease, we know from the pre-antibiotic era that the natural history of that is that about a half of patients would succumb to their disease, whilst another half would, after a long struggle, cure themselves and actually completely recover. Treatment today, 4-drug treatment for drug-sensitive TB is completely effective, and there's only a 2% relapse rate. So that's the other form of effective control there. And then, of course, while patients have pulmonary TB, they're infectious to others, and that keeps the cycle of infection and reinfection continuing in the community. Now, the mystery of the natural history of TB infection was nicely summarized by George Comstock, who was the grandfather of TB epidemiology from Johns Hopkins University. And he said very eloquently that TB is an infectious disease with an incubation period from a few weeks to a lifetime. And in a sense, the key role of the host immune response in shaping the outcome, not just of TB, but of many other intracellular infections, was actually foreshadowed by Hippocrates, who said, I would rather know what sort of person has a disease than what sort of disease a person has. And it's really this interplay between the host immune system and the pathogen that led me to develop this sort of fascination with the immunology of TB. So the host factors that cause progression from latent infection to TB disease, to use the Hippocrates, what sort of person has the disease? Well, we know that if you have HIV infection, or if you're having iatrogenic immune suppression, you're much more likely to progress to TB disease. If you have HIV, the risk of progression is not 5% in a lifetime, but 10% per annum. There are also other factors that promote progression that we understand far less well, such as very young age, poor nutrition, and poverty. TB control is also based on the natural history of TB, and we intervene at 3 main points. The first is treatment of active TB disease. The second is BCG vaccination, which has been believed to act at this site, preventing progression from latency to active TB. And thirdly, we identify and treat people with latent TB infection, or LTBI. And before leaving this slide, I'd just like to remind us all that this entire natural history, this understanding that we have, is based on the 100-year-old tuberculin skin test and chest X-ray. So we might still have a thing or two to learn about it, as we'll see. Now this slide really, this diagram summarizes the conceptual framework of my research over the last 15 years. And it begins with hypothesis-driven basic science, which in my case was the study of the immunology of intracellular infection, which can lead to improved understanding of the spectrum of host immune response involved, pathogenesis, protective immunity, and vaccine design. And I'll show you in which ways the research I did at the bench in terms of basic immunology has had those sort of outputs. And it's hypothesis-driven basic science that underlies and enables us to then develop and validate new tools and biomarkers. And it's these new tools and biomarkers that are required not just to improve clinical diagnosis and clinical management, but they're also essential for the evaluation of new vaccines and new drugs. Finally, once you develop new tools and biomarkers and diagnostics, you can apply them at the population level and then see the societal impact. And I'll take you through later on the sort of societal impact that the outputs of our research have had to date. At the very end of the talk, I'll come to this aspect, which is how, when you apply new tools to the diagnosis of disease in routine practice and in epidemiological studies, you can then begin to refine and redefine the understanding of the natural history and epidemiology of disease. So the invention of a new test such as the T-cell based test, for example, was described by Peter Openshaw as something like when you have a new microscope. You can then go and address disease in a different way and learn new aspects about etiology and pathogenesis of disease. And at the end of the lecture, I'll show you that's exactly what we've done, as those discoveries have brought us back to the bench. So I'm going to begin with the hypothesis-driven basic science that led to a series of outputs that I'll quickly take you through now. And when I first approached Adrian Hill and did the MRC training fellowship with him in the early mid-90s, he was working on malaria immunology. And I knew at the time that my medium and long-term goal was to work on TB immunology. And he kindly agreed that after a year or two of working on malaria, I could then have a stab at establishing TB immunology research in his lab and in Oxford. But I set out studying the immunology of malaria, and at that time, his team had just identified the first CD8 cytotoxic T-cell response to P. falciparum malaria. And these were class 1 restricted CD8 CTL that were recognizing liver stage antigens presented at the liver stage of malaria. And the idea was that if we could enhance or increase this cellular immune response at the stage of the liver, we might be able to eliminate malaria parasites before they break out of the liver and into the bloodstream. So it's really a very potentially attractive site at which to intervene. And CD8 cytotoxic T cells are adapted for recognizing virus-infected host cells or malaria-infected host cells. In other words, host cells where the pathogen is making its proteins in the cytoplasm, and then they get accessed by the class 1 antigen processing pathway and presented, the peptide fragments are presented by HLA class 1 molecules to the T cell receptors of CD8 cytotoxic T cells. So my goal was really to try and identify these cells, and the methods we used at the time were as follows. We were trying to identify these little blue cells in the blood, the blue ones being the antigen-specific ones, which are a tiny fraction of all the T cells in the blood. We just wanted to identify the ones that were specific for a few peptide targets from a few antigens from malaria. So how could we identify such a small number of cells? And the techniques used at the time involved re-stimulating those cells in vitro with your candidate peptide target until those cells grew out to large numbers, sufficiently large that you could then test them for their effector function. And in this case, we were testing for cytotoxicity using radiolabeled target cells. So we just measured how effectively the cells killed target cells that were coated with the peptide target. And these studies essentially were carried out in naturally exposed Africans to see if we could find these T cells in their circulation. The first study I did was in the Gambia, together with Hilton Whittle and Brian Greenwood, and there we found a series of new epitopes from the liver stage antigens of malaria. That was followed by a study in Tanzania with the Swiss Tropical Institute, who I came to know whilst I was a SHO in Basel, and they had a research station based in Ifakara in Tanzania, which at that time was the most malarious place on earth. And there also we identified these cytotoxic T cells. The rationale then was to use these epitopes to see whether new malaria vaccines that were designed to induce these T cells were indeed inducing them or not. So we used these epitopes in a study that I went to do at the Walter Reed Army Institute of Medical Research in Washington, D.C., where they had a live sporozoite challenge model for human volunteers for malaria, and I evaluated the immunogenicity of New York Vaccinia 7, this anti-malaria vaccine that was a new vaccine at the time. And so by this time I'd developed some real interest and experience in working with CD8 cytotoxic T cells, and this was the angle from which I came into tuberculosis immunology. Now this slide shows you the red rods of the tubercle bacilli being taken up by the host cell where they live in the body, so the macrophage. They're engulfed, and then their antigens are processed, but the bacillus remains in the phagolysosome, and the antigens are not presented through the class 1 pathway, but they're presented through HLA class 2 and they're not presented to CD8 T cells, but they're presented to CD4 T cells. And so the predominant host immune response to TB has always known to be CD4 helper T cells that you can see here. And when they recognize TB antigens on the surface of the infected macrophage, they release interferon gamma, which activates the macrophage, helping it to try to suppress or destroy the bacillus. So this is in contrast to the CD8 T cells I've told you about, which recognize virus-infected cells or malaria-infected liver cells. But it had been observed just a couple of years previously that in the mouse model of TB, CD8 T cells, class 1 restricted CD8 T cells, were essential for protection against TB. So this led to a bit of a quandary, because as far as we knew, they didn't exist in humans. So I set about trying to find them. And the approach I used was similar to that I've just described for malaria, as I've shown you here. But unfortunately, in this case, when I tested for cytotoxicity, there was no success. So I reasoned that actually perhaps we could measure an alternate effector function. Instead of just measuring how these CD8 cytotoxic T cells might kill their target cells, maybe we could measure interferon gamma that they might release, because they release cytokines as well as killing the target cells. And so it was interferon gamma that I set about trying to measure from these CD8 T cells. Fortunately, this proved to be a useful strategy, because using an ELISpot assay to measure the interferon gamma, I was able to identify CD8 T cells in TB-infected humans for the first time. And since that paper was published a decade ago, every new TB vaccine that's since been developed and is undergoing evaluation has been designed to induce CD8 cytotoxic T cells as well as CD4 helper T cells, because they're now recognized to be an important limb of the host immune response to TB. And during those studies, I noticed that the methodology I was using appeared to be much more sensitive for measuring small numbers of antigen-specific T cells than the traditional cytotoxicity killing assay. And so then I asked myself the question, well, if it's so much more sensitive, could we possibly measure these rare antigen-specific T cells direct from peripheral blood? So the ones that are there in the bloodstream, can we measure them directly? And so that's what I attempted to do, using what I termed the ex vivo enzyme-linked immunospot, or ex vivo ELISpot, to measure these T cells without any previous in vitro stimulation. And if that worked, that means we would then be able to measure these T cells without the quantitative and qualitative biases that are introduced by in vitro culture, which is in the end an artificial system. And trying this out in people who'd recovered from influenza, which is a well-understood model, I studied a series of influenza antigens and found that, yes, you could actually measure these T cells direct from peripheral blood without any sort of stimulation. And this really opened the way to now high-throughput quantification and characterization of T cells direct from peripheral blood for a number of pathogens. We did that then extensively in tuberculosis, and it since became a benchmark for what we call epitope mapping in a range of intracellular pathogens, including HIV vaccine design. Then we also applied this approach to measuring the immunogenicity of new malaria vaccines. And a vaccine that had just been, was being tested at that time was RTSS. And we used this approach to measure the T cell immunity induced by that vaccine, which was quite substantial as it happens. And that vaccine is now the lead candidate for the first malaria vaccine, and it's undergoing phase 3 trials in Africa currently. And this approach really became also the benchmark for immunogenicity testing of new vaccines in the field for malaria, HIV, and TB, those three being the vaccines that are all T-cell inducing experimental vaccines. And so to the next stage of this sort of conceptual framework of our research program, the studies I'd done so far, I was able to exploit them to develop and validate new tools and biomarkers to try and improve diagnosis and clinical management. Now, at the time that I was doing this work with the T cells, a group at Stanford were using genome-wide microarrays to compare the entire genomes of M. tuberculosis, M. bovis, and the BCG vaccine. And the output of their research is this diagram, which is the genetic history of the BCG vaccine. And what we now know is, from this research, is that in the early 1920s, when Calmette and Guérin, after whom BCG is named, were passaging M. bovis in vitro, it was becoming progressively more attenuated. And at one point they found, when they inoculated it into guinea pigs, that the guinea pigs no longer died. So they decided at that time that it was no longer virulent and could be used as a vaccine. And that was in 1921. And that attenuating event in BCG, we now know, was the loss of a 9-gene segment of DNA that occurred spontaneously sometime before 1921. And that region of DNA is called region of difference 1. And the key point is that it's absent from all strains of BCG vaccine, but it's present in M. tuberculosis and in its close sister, M. bovis, which causes bovine TB. And fortunately for us as immunologists, region of difference 1, 2 of the open reading frames in that stretch of DNA encode ESAT6 and CFP10, which happen to be the strongest targets of the T-cell immune response in TB-infected humans and animals. So this just shows the same thing really in a cartoon form, that M. bovis and M. tuberculosis have RD1, and they express these T-cell antigens ESAT6, CFP10, while BCG lacks it, and all clinical strains of MTB have RD1. Now, this specificity of these antigens was very important, because the tuberculin skin test that I mentioned earlier, or MORN2 test, essentially is when you inject tuberculin PPD, which is 200 proteins from TB. But those 200 proteins are widely shared between TB and the BCG vaccine. So people who've been previously BCG vaccinated will mount a delayed type hypersensitivity immune response in the skin to the tuberculin PPD and come up falsely positive, even though they don't have TB infection. So the important point about ESAT6 and CFP10 coming from RD1 as they do is that this opened potentially a new approach to get a specific diagnosis of latent TB infection, which would not be confounded by BCG vaccination. So we combined now these highly specific T-cell antigens together with our highly sensitive T-cell assay to formulate the hypothesis that ESAT6 and CFP10 specific T-cells are an accurate marker of TB infection. And the first study we did was in patients I was looking after on the infectious disease unit in Oxford with Chris Conlon and David Worrell, and TB patients that I was seeing in the clinic at Northwick Park every week with Jeff Pasval and Rob Davidson. And we found a very high diagnostic sensitivity of the assay. Over 90% of patients were positive. We also noticed that their household contacts who were skin test positive were also ELISpot positive. And this led Peter Barnes from Texas to call this the 100-year upgrade for diagnosis of latent TB infection. Now that was very encouraging, but we now face potentially an even bigger problem, which is how can you prove that a new diagnostic test is better than existing tests when there's no gold standard? So what we did was we exploited the central tenet of TB epidemiology, which is that TB transmission is promoted by proximity and duration of contact with an infectious source case. And the key determinant of infection is the amount of time you spend sharing room air with an infectious source case. And so we formulated this postulate, which is that if ELISpot is really more sensitive and specific than the skin test, it should correlate more closely with the level of exposure to TB than the skin test does, but it should be independent of BCG vaccination status. So we set about doing a series of detailed, blinded epidemiologic studies comparing the relationship of ELISpot results and skin test results to the intensity of TB exposure. We did this not just in adults, but we did it in 2 of the most important high-risk groups in whom we need rapidly to identify latent infection when it develops, and that's to say young children and people with HIV, because that's the target population in which a test of latent infection needs to work. It was at this time that I happened to meet John Watson, the Director of Respiratory Infections at the Health Protection Agency. I met him at a conference at the RSM, and I mentioned to him the sort of studies that we were needing to carry out to validate this approach. And he pointed me up the M1 in the direction of Leicester, which at that point was experiencing Britain's largest institutional outbreak of TB since the Second World War. There were 70 secondary cases of active TB at the school and 254 cases of latent infection. And there were three key features of the outbreak for us. The first being that it occurred in an enclosed environment. The second was that it was all caused by a single infectious source case. And the third was that the school had electronic school timetables, which meant that we could compute the exact amount of time that each child spent sharing room air with the source case. And we found that the ELISpot and skin test results agreed with each other by and large, but that overall ELISpot correlated statistically significantly better with TB exposure than the skin test. And it correlated significantly better with both proximity and duration of exposure to the source case. And this table really just shows you also that unlike the skin test, which was confounded by prior BCG vaccination in these children, 80% of the kids were BCG vaccinated, the ELISpot was independent of BCG vaccination status. So we then did further studies in children of this sort of study design. The first was in the city of Modena in northern Italy, where a mother with multi-drug resistant cavitary smear-positive TB gave birth to a healthy baby boy on the maternity unit. And it was only 10 days after discharge that her GP picked up this very advanced TB. And we essentially screened all the newborn babies, visitors and healthcare workers and mothers on the unit, and again we found that the ELISpot correlated significantly better with exposure to this mother during her 4-day admission than did the skin test. We then did studies on adults as well. One was a community-based study in London where we showed that again ELISpot correlated better with TB exposure than the skin test. And another was with Peter Barnes in Texas, where there'd been increasing concern about transmission of M. tuberculosis across the US-Mexico border. So we did a study of 413 people in the community, and again, the ELISpot here correlated statistically significantly better with TB exposure than the skin test. Most recently, we're just writing up now a study we've been doing with Liz Corbett in Harare in Zimbabwe over the last 5 years, looking at the reliability of ELISpot for diagnosis of latent infection in HIV-positive household contacts, and it turns out that it's not adversely impacted by HIV co-infection, unlike the skin test, which is completely useless in that situation. So that was people who've had specific exposures to TB by virtue of household or workplace contact. What about people who don't have such a history of specific exposure but just live in a high-burden country? What's the prevalence of infection by ELISpot in such populations? To answer that question, we went to Bombay, where we screened 100 adults who were healthy with normal chest x-rays and no history of TB exposure, and it turned out that 80% of them were harboring latent infection, as denoted by ELISpot. The assay also holds great promise in active TB. And again, in active TB, it's people with HIV co-infection and young children who have the worst morbidity, the highest mortality, and are the hardest to diagnose. So we addressed that problem head-on, and we did a study in Lusaka in Zambia, where we studied a series of adults with smear-positive pulmonary TB and HIV co-infection, and we found the diagnostic sensitivity remained high. And we also used this assay to try to help in the evaluation of a very difficult yet needy population, and that's to say young children with HIV co-infection and suspected of active TB in sub-Saharan Africa. And we did this study in District General Hospital in KwaZulu-Natal, and it was a study of 300 children whose presentations were incredibly difficult to diagnose, because clinical HIV in the tropics can very closely mimic clinical TB. So it's very difficult to distinguish one from the other. And of course, they often accompany each other simultaneously. So this study was probably the hardest test you could give for any diagnostic test for TB. And we found that the diagnostic sensitivity remained high in these children, and that the test was not adversely impacted by HIV co-infection, very young age, or malnutrition. And all those factors render the skin test virtually uninterpretable. So the next part of the talk is going to be to describe really what the impact of these new tools has been on society. And in terms of societal impact, we're talking about the impact on public health policy, lessening disease burden, and ultimately health economic benefits as well. But I'm going to begin with the first two individual patients to benefit from the output of my research, which in some ways was the most satisfying point of my research career. The first was that this is the X-ray of the mother who gave birth to the baby boy in the maternity unit in Modena with multi-drug resistant TB. Her husband, of course, was heavily exposed. He was taking azathioprine for inactive Crohn's disease, which is an immunosuppressive agent, and his tuberculin skin test was negative, and it's often negative in people taking azathioprine. But he had been heavily exposed. Fortunately, his ELISpot was positive, and that mandated, as per our study protocol, that he would have a high-resolution CT scan. And remember, he was asymptomatic with no cough. This is what his CT showed. He had an early manifestation of a tuberculous cavity, and although this was small, that cavity would already be teeming with millions, if not billions, of multi-drug resistant tubercle bacilli. So we were in the unique position of being able to offer this man anti-MDR TB treatment before he'd even so much as coughed. So essentially what we did, we prevented a secondary outbreak of multi-drug resistant TB in Modena. And Modena, as you'd know, is famous for its balsamic vinegar and as the place where the Ferrari car is designed and produced. And unfortunately, the only thank you gift I've received so far from Modena has been the vinegar and not the car. And I'm still waiting. The second patient to have benefited also was in Modena, and she was a middle-aged woman with hairy cell leukemia who had been languishing on the wards with a fever of unknown origin and a pleural effusion. All tests were negative. And so what was carried out was a blood ELISpot, which was positive, and an ELISpot directly from the pleural effusion, which was also strongly positive. And this accelerated her diagnosis of TB, and she was able to begin anti-TB treatment and did extremely well and recovered. So during the series of inventions in Oxford over the years in the development of the diagnostic ELISpot, I'd filed about half a dozen patents through the University of Oxford, and all of these are now granted in Europe and the US. And these patents were licensed in to an Oxford University spin-out company which commercialized the assay into a regulatory approved and quality assured diagnostic test kit. And that test kit, known as T-Spot TB, is based on the state of our research, the state of the assay that we developed as of 2003, 5 years ago. The same antigens I described to you as we published those early papers in the early 2000s, they were also incorporated into a whole blood ELISA assay, so an alternate means for measuring interferon gamma release from T cells. And that assay is called QuantiFERON TB Gold in tube, made by Celestis. And the two assays collectively are known as interferon gamma release assays, or IGRAs. And as a result of the studies I've described to you, NICE issued a new set of TB guidelines in March 2006, and based on these various studies with these IGRAs, they recommended for the first time using a test other than the skin test. And they recommended to use the blood tests in individuals who've already tested positive by the skin test, in other words, to be sure that those people are TB infected and not just BCG vaccinated with a false positive skin test result. And they recommended going straight to the blood test in individuals in whom the skin test is unreliable. So Britain was the first country in Europe to issue such guidelines, and in the last 2 years, 14 European countries have followed suit, all with essentially the same type of guideline, and Canada as well. In the US, of course, things are done slightly differently, and the Centers for Disease Control there has recommended using the blood tests up front and dispensing with the skin test altogether. The reason for the difference is that NICE opted for the most cost-effective model. So really the main remaining question about these interferon gamma release assays is whether they predict progression to TB in someone in whom they've diagnosed latent TB. And this is the first example of such a case of progression. It's the story of the baby born to the mother with MDR TB in Italy, and the baby was born well, was given pyrazinamide and ethambutol preventative therapy because the bacillus was resistant to rifampicin and isoniazid. The child's skin test was 0 millimeters, so persistently negative over the first 18 months of life, but its ELISpot was weakly but clearly positive. By 2 years of age, this child had developed fever, failure to thrive, unilateral hyaline-lymphadenopathy, and a cough. And gastric aspirates grew multi-drug resistant TB of exactly the same DNA fingerprint as the mother, thereby confirming that actually the child had indeed acquired a latent TB infection perinatally, carried it for 2 years. The preventative therapy hadn't worked, that is, as it often doesn't for multi-drug resistant TB, and then progressed to active TB disease. How are we going to use these tests in active TB? Because, of course, as immune-based tests, they're tests of infection, and they don't distinguish between latent infection and active TB disease. But of course, TB infection is a prerequisite for TB disease. And therefore, potentially, we could use the tests to rule out infection. And if you can rule out infection, you can certainly rule out TB disease. But to do that, you need a test of very high diagnostic sensitivity. Now, over the last years, we've obviously made further advances since the assay was commercialized. And this paper really shown here is about the next generation assay, which incorporates not 2 but 3 antigens from region of difference 1. And the new antigen incorporated here significantly boosts diagnostic sensitivity without compromising specificity, offering the possibility now for the first time to actually exclude potential diagnosis of TB where that is suspected. But you can also exploit another immunological principle here, and that is the fact that pathogen-specific T cells home to sites where the pathogen is. They home to sites of active disease. So we wondered whether if we looked at fluids from disease sites, could we actually see increased frequencies of TB-specific T cells there and thereby diagnose active TB disease as a rule-in. We did that first in a series of patients with pleural effusions, all of whom were positive in the pleural fluid, and patients with non-tuberculous pleural effusions were all negative. We then carried out a study based on a similar principle in patients with smear-negative pulmonary TB. So patients, these were in northern Germany, who had suspected pulmonary TB, underwent bronchoalveolar lavage, cultures were awaited, but the diagnosis was unknown. And when we did the ELISpot on the BAL fluid, we found that it was packed full of T cells specific for these antigens, so we could accelerate their diagnosis. And finally, we addressed what remains to this day the greatest clinical challenge in TB, which is tuberculous meningitis. And to do this, we did a collaboration with the Christian Medical College in Vellore in South India, and we measured the frequency of these antigen-specific T cells in cerebrospinal fluid. And we found that the sensitivity in patients with TB meningitis was 90%. And by contrast, patients with non-tuberculous meningitis were uniformly negative. So, whilst applying the tools at the population level, and you can learn more about disease and refine and redefine your understanding of natural history. And that's really the next part of the talk, and how that in turn leads you back into hypothesis-driven basic science with new hypotheses. So back to the natural history of TB infection, as it's been known for the last 80-odd years since development of skin test and chest X-ray. This data here is just the follow-up data from a group of the children at the school in Leicester. And the results, this is their ELISpot results over an 18-month period of follow-up after the outbreak. None of these children had preventative therapy. And as you can see, on the y-axis is the strength of response. And circled in green are those children who had borderline or weakly positive skin tests accompanied by a positive ELISpot result. And their ELISpot results remain positive over the 18 months of follow-up. But there's another group of children here with completely negative skin test results, whose ELISpot results went negative by the first follow-up time point at 6 months. Now, to an immunologist, the disappearance of effector T cells from the circulation, disappearance of antigen-specific T cells, suggests that the antigen stimulation in vivo has ceased, and indeed that the pathogen may now have been cleared. And that was our interpretation of that data. And in fact, we've seen that phenomenon now in 5 separate outbreaks around the world. And when the editorial about our bold hypothesis appeared, I looked at the title and I thought, well, maybe they're referring to me here. But fortunately, the editorialists were referring to our hypothesis, and they were essentially agreeing with our interpretation of that compelling, provocative data. So we've been able to add a new limb to the natural history of TB just here, showing that people probably can actually clear an infection spontaneously, and that had not previously been imagined. Next, we asked ourselves, can we use an improved tool to reevaluate the risk factors for TB infection? And specifically, since ELISpot distinguishes TB infection from BCG vaccination, can we use it to find out whether BCG vaccination itself affects risk of TB infection? And to do that, we went to Istanbul and we did a study of 1,000 child TB contacts recruited from over 300 households. And we followed them up for 2 years. And the baseline data that we had showed that those children, 80% of the children had a BCG scar, so had definitely been BCG vaccinated. And the data showed that actually the children who didn't have a BCG scar were significantly more likely to have acquired infection in the setting of exposure. And quantitatively speaking, we worked out that the presence of a BCG scar conferred a 25% risk reduction in acquisition of TB infection. So this also added further new information to our understanding of the natural history, because now we realized that vaccination acts not only by preventing progression from latent TB to active TB, but it can actually prevent acquisition of infection in the first place. And this has very important consequences for TB vaccine development and evaluation. I've been intrigued for several years by the sort of immune suppression that happens during active TB. So when patients have active TB disease, it's been noted that their cellular immune systems are suppressed, and specifically their CD4 helper T cells have impaired proliferation, impaired secretion of cytokines, particularly interferon gamma. And we postulated that a recently identified subset of T cells known as regulatory T cells, which suppress overactive T cells in the body, we hypothesized that they may be playing a role in this process in TB. And we were able to identify that these T cells, which were CD25 high and FOXP3 positive, were substantially expanded in the blood of TB patients, and even more expanded at disease sites. And we further were able to show that these cells actually suppressed interferon gamma secretion by the TB-specific T cells. And so, really, over the last decade and a half of immunological research, we've been able to identify and characterize a series of new T cell subsets that had not previously been recognized to be involved in the host immune response to TB. The last group of T cells to appear there are CD1-restricted lipid-specific T cells, which weren't first identified by us, but by other groups. But we're now also working on those, and particularly the subset of those that are specific for mycolic acid, which is the predominant component of the lipid-rich cell wall of MTB. Gamma delta T cells are also important in the host immune response to TB, but we haven't investigated those just yet. So we know that these new IGRAs cannot distinguish active TB disease from patients who've undergone successful treatment for TB. You can't tell the difference with the IGRA assay. So we asked, is there a way to be able to tell the difference here? Because this would be pretty useful, as I'll explain shortly. And so, if you'll just bear with me for a minute of sort of background immunology. In broad terms, you can think of the cellular immune response to pathogens as consisting of 3 different types of pathogen-specific T cells. So on the one hand, you have these interferon gamma secreting T cells that only secrete interferon gamma. That's the only cytokine they release, and they're called effector T cells. And they are driven and present, they're driven by high loads of antigen, and they predominate when people have a high antigen load, high pathogen load, and haven't yet started treatment. Then you have what are called memory effector T cells, which secrete not just interferon gamma, but also interleukin-2. And those T cells tend to predominate when the antigen load is at a lower level and protracted, but low or moderate levels of antigen load. And finally, you have what are termed central memory T cells that only secrete interleukin-2. And the predominance of these different populations of T cells has been elegantly worked out by viral immunologists who've shown quite systematically that in primary CMV disease and in progressive HIV disease, where you have high viral load and antigen load, it's the interferon gamma only secreting effector T cells that predominate by far. And then when you start antiretroviral therapy and your antigen load declines, you have a mixed picture. And you have now dual cytokine secreting T cells appearing, and for the first time you get the appearance of a few interleukin-2 only secreting T cells. So Kerry Millington in the lab applied these principles to the study of TB, and she looked at patients with active TB who had, as you can see here, a large number of interferon gamma only secreting T cells shown in white and some dual secreting T cells in gray. And then when she restudied patients during and after treatment, she saw that the proportion of dual secreting T cells had massively expanded, and these were now vastly predominant. The interferon gamma only secreting effector T cells had all but disappeared, and for the first time we had the appearance of interleukin-2 only secreting T cells. So this immune profile, if you like, of individual antigen-specific T cells measured at the single cell level indicates to us that by measuring polyfunctional T cells, we might be able to develop accurate biomarkers of treatment response. That would not only be useful for monitoring TB patients during treatment, but it will actually be essential for validating new anti-TB drugs as these are tested in clinical trials. And we are now applying this approach to a clinical trial known as ReMox-TB. So it's a large phase 3 trial of moxifloxacin, which is the drug that's closest to getting a license for anti-TB treatment, and it's being carried out in Durban, and moxifloxacin is replacing ethambutol in these studies. And the expectation is that the patients will convert their sputum cultures quicker, and that our biomarker will also show that improved treatment response. That's being done in collaboration with UCL. So finally, just a little glimpse of the future and what we're actively engaged in currently. So our current program of research, funded by the Wellcome Trust, is to now elucidate, really for the first time, the immune and genetic factors that determine very early after exposure to TB why some people actually acquire the infection and others don't. Because of course it's quite interesting that 60% of household contacts of infectious TB patients don't get infected. So you have to ask yourself what's going on, and we're going to be looking at that because they're obviously not holding their breath. They're breathing in infectious droplets. Secondly, we're going to be studying this new phenomenon we've discovered of acute resolving infection in humans as well as in cattle with Martin Vordermeyer and Glyn Hewinson at the VLA. Thirdly, we want to try to understand much better what are the what sort of biomarkers can we identify that will be able to allow us to risk stratify people with latent infection. Currently, people with latent infection are given preventative therapy even though we know that only 1 in 10 will develop disease. If we could have a biomarker that could risk stratify better, we might be able to just treat 5 to prevent 4 cases. So we're measuring a range of different immune baseline biomarkers for their prognostic predictive value. And we're also studying, together with Alan Winston, Onmin Kon, and Mark Lipman, the impact of antiretroviral therapy on immune reconstitution to TB, to try to understand better what are the protective immune responses to TB that get reconstituted during antiretroviral therapies, and which ones fail to get reconstituted. And aim 5 is to do immune profiling of individual T cells to be able to compare in our clinic at St Mary's and with collaborators at Northwick Park and the Royal Free, exactly what is the can we identify immune profiles that can distinguish for the first time active TB from latent TB infection using the sort of principles of cellular immunology that I've just recently described to you. And so as you can see, we've sort of come full circle, because the new insights we've gained by applying our new tools have generated new hypotheses, deepened our understanding of the natural history of TB, and have really brought us back to the bench and back to hypothesis-driven basic science with a set of new hypotheses. And to achieve our next set of goals, I'm very fortunate to have recruited around me an outstanding interdisciplinary team of scientists, medics, and research nurses whose enthusiasm and dedication is really a pleasure to behold every morning. And I'd like to dedicate this lecture to what Dame Margaret Turner Warwick termed last year during her Snell Memorial Lecture at the British Thoracic Society as the courage of TB patients. Now, Edvard Munch painted this portrait of his sister in 1890, obviously in the pre-antibiotic era, when his sister had pulmonary tuberculosis, and he painted it in the same year that Robert Koch developed the skin test. And pictured here is the floating sanatorium of the Bellevue Chest Clinic of the city of New York from the 1930s, also the pre-antibiotic era. This was really a floating TB sanatorium. And, you know, today, in many ways, we're back to the future, because in patients with multi-drug resistant TB and XDR TB, they're essentially relying on their own immune response and their own resources to heal themselves, because our drugs, to be honest, are doing very little. And so I really think that you know, what I'd like to do is to dedicate the lecture to patients with TB, both past and present, particularly those whom we're failing by not providing them with adequate interventions and drugs. And I also think that really, you know, it's our mission as a group to continue research to be able to finally give TB patients a better deal, which is what they really deserve. Lastly, I'd like to thank all our collaborators around the world, most of whom I've mentioned as we've gone along. And particularly, I'd like to thank my wife, Maria, for her faith, support, and forbearance, which is a nice way of saying her ability to put up with me. Of course, my parents, Karthar, a scientist, and Mira, a physician, who together planted in me the seeds of intellectual curiosity, perseverance, and empathy and compassion when caring for our patients. And finally, the Wellcome Trust for funding all these studies over the last 13 years. Thanks. If you want, yes.